All right, hey, welcome back to Mechanical Pros. I'm here with Jeff, and we are on location. Jeff, tell me where we are and what we're doing out here.
Well, what we're at is we're at a satellite station, which is a pumping station for a small community here in Middle Tennessee. Brought some unique challenges to us.
Okay, so we're pumping domestic water here?
Correct. This location here, what they've done in the past is you would have the treatment plant that would pump the water to the tops of these hills up here, and there's serviceable containers up there. And what it would do is it would gravity feed domestic water into it before this pumping station came online.
Okay. So this is a pumping station in a residential area. We're taking in domestic water from tanks in hills, and then when it's gravity fed back here, we repump it and distribute it to where it needs to go.
Correct. What we do is we take the water that comes out of the tanks and we go into an underground facility over here. And what it is just a large basin. And that allows us to draw from that basin and get a regulated output out of the pumps.
And then, so what were some of the challenges that we were faced with in this? It's a small building, but we got a ton of water coming through this facility and a ton of power coming through this facility. So what does that mean for the neighborhoods and for managing the water pressure and then also power quality and such?
There's a total of 1,800 horsepower worth of pumps in here. So getting the amount of power that we required and then not polluting that power, because it is residential, and so we have to be good neighbors and good stewards of the electricity that we use. Yeah. So we had to attenuate harmonics, we had to meet design criteria, we had to meet a footprint. Yeah, which was an unbelievable challenge.
Yeah. So tell me this. We talk about harmonics, power quality a good bit, and all these pumps are going to be variable speed. We provided the variable frequency drives.
Correct.
That control these pumps here. And you said they're 600 horsepower each?
600 horsepower each, a total of 1,800. We run in an N+1 most of the time, which means that we have 3 pumps. We run one at a time on normal operating days. During the weekend, when people are home, watering, doing that type of stuff, we do go ahead and start a second pump, but we always hold one in reserve.
Okay. But so we got a lot of residential area around here, and we want to make sure that with all our variable nonlinear power loads, we're not pushing that back into the community and creating havoc amongst residents.
So basically what we ended up with is the basic design of the drive that we supplied here has a 33% harmonic content at drive terminal. So we had to multiply that by 3 and then attenuate that. So we did take some of the design, we kind of broke out and we added an active matrix harmonic filter.
Okay. Cool.
But also on the drives, we used Yaskawa's industrial version, which gives us a little bit better harmonic attenuation simply by adding a 3% line reactor to the front end. The drive itself has 5%, so we have a total of 8%.
Okay, cool. Let's take a look at the pumps, talk about, just an overall what they're doing.
Correct.
And then look at the drives and then that harmonic filter. We don't see a ton of those, but it's always exciting, and we've been talking about it a good bit, so it's good to see one out in the field. All right, let's jump inside. All right, we're in the electrical room, and tell me what we got laid out here, and it looks like we got some cool stuff.
Well, and like I was saying, obviously we had a really, really big challenge trying to get all this equipment. We have 1,800 horsepower worth of power that has to come in here. So we had the main switch gears that's over here behind us, but we also had to be able to put 3 of these drives in here. The harmonic filter over here in the corner that really is the one that really does all the work to attenuate our harmonics. Now, as we go on, I want to go ahead and I want to explain to you the equipment that we have.
Yeah.
So what we did, John, is we got with Yaskawa, and we basically told them, we gave them the footprint. And I said, we don't want to impede on our cooling capability, but I still want to be able to do everything that we need to do. Yeah. So what they did is they repackaged their G800 drive. Now this is Yaskawa's industrial offering. It's a little bit outside the commercial that we normally talk about. This drive here is based more on a constant torque output, just simply because of the amount of head that we need to create on these pumps.
Yeah.
So I'm going to go ahead and I'm going to swing the door open. Here on the front is the keypad where any operator will actuate. He can collect all the data. This first screen that you see on here gives him all the pertinent data when he comes in. He'll come in, he's able to see how fast that the building is telling it to run or the basin is telling us to run. Tells him how fast we're actually running, and then it gives him a current load as well. So he really doesn't have to interface too much with this.
Okay.
All of this is done with a SCADA system. So everything is wirelessly transmitted back to the main and as well as to his iPad. So he can come in and control these pumps through his iPad. So we do have remote controls. We'll talk about the control system here in a little bit.
Yeah.
But I want to go ahead and take some time and open up the door. And here on the front end, John, we see that we have the main service disconnect. Now this is a 1,000 amp breaker. And then what we do is we come out of the 1,000 amp breaker and we go to 1,400 amp fuses to protect the front end of the drive. Now, if you'll notice, as we come out of this disconnect, we come down and we hit the 3% line reactor I was talking about. When we move over to the other side, I'll show you the drive, but this right here gives you a good idea of our input power scheme.
So the line resistor?
This is the line reactor down here. This adds 3% impedance. So what this means is I'm adding resistance to that harmonic waveform to try to slow it down before it hits the active filter. I'm trying to give it a better wave sign.
Yeah.
Okay. So that's what that does. Now, duplicate to that would be the 5% that I already have internal in the drive itself. So when you add the two together, that gives me 8%. That equates to, remember we talked, 33% at input terminal of the drive. The 8% impedance that we have takes our 33% and knocks it down to 21%. 21% harmonic content times 3 is much more manageable for the harmonic filter.
Okay. So we're knocking it down to something that's manageable for the filter.
Correct.
And does that help us size the filters? Can the filter be sized smaller?
Yes, we were able to size the filter smaller because it was kind of a trade-off.
Yeah.
We really wanted to go to the matrix drive that Yaskawa offers, but they didn't have it in the horsepower that we required. So that's when we opted for the GA800 multi-layer input diodes with the reactor. Okay, so now if we come over here and we shut this door, over here is the drive itself. So like I was telling you, Yaskawa does a really good job of informing its operators the condition of the drive without really having to interact too much. So if you look at the screen down here on the bottom, and Yaskawa came out with this year, but it's the blue smiley face. Yeah. You see a blue smiley face, that means that the drive is operating the way it wants to. When you see the green light that's up above it, that means that that drive is actually running.
Okay.
If we were to have a fault, the upper right-hand corner would turn red. And then we would get an indication.
Okay, yeah. So we got green is running, blue is happy, and then if it was something was wrong, a fault, that'd be red right here.
Correct.
Okay.
So they're really good with visual indications, so that you don't always have skilled technicians that are looking at this, but that allows them to transfer information to us so we can tell them whether what they're looking at is benign,
yeah,
or whether or not it's an actual problem. So we'll move over to the active filter now. Okay, so John, what we have here now is the active filter. This is the part that we were talking about outside, about attenuating the harmonics and being good neighbors. What this actually does is it captures that remaining harmonic that we did not capture through the impedance of the drive itself, and it takes that and it filters. And if you'll notice up here on the screen, it gives me a total load. Well, right now I'm only running one pump. It's a Friday afternoon. Everybody's at work. Not a lot of people using a lot of water. So we're only running one pump, and we're running it fairly slow. I'm only drawing an average of about 240 amps, okay? But if you'll notice, the second line down that says load harmonics, that's how many amps have polluted waveform that we're having to correct.
Yeah.
So it tells you what you've got coming in, and then the next line down tells you how many output harmonics. And so you'll notice I'm at 0 amps right now in harmonic content. So the active filter, that's how you know it's doing its job. Our actual, what we wanted to do is we wanted to get down to about 3% of load harmonics, of which we ended up, by the time we get done, we found out when we only run one, we're at 0 amps. We're actually cleaning it back up, almost sinusoidal.
Okay. So this is each leg?
This
Leg
is
1, 2, 3?
Correct.
And so we got 201 amps still coming in.
Correct.
And then about half of that is dirty.
It's dirty.
And we're cleaning it up, and we're putting out 202 amps, and it's clean.
Yeah, it's clean power, but then the other thing that you'll notice is we have a little bit of a phase imbalance, or a current imbalance.
Right.
And the reason why you have a current imbalance...
Because you got 200 on leg 1, 250 leg 2, 230.
Right.
Yeah.
And the reason why you have that is because, believe it or not, there's a substantial amount of single phase load here, okay? So we're pulling that load, it's about 40 amps worth. So we're pulling that load off of legs 2 and 3, And that's why the current is low on number 1, because our voltage is much higher than the other 2 legs. So the lower the voltage, the higher the current. But we also had to protect that single phase load with this, so that's why we had to incorporate it into the filter. So as they go along, they have a constant metering of this device as well, just like they do the drives. They can come in and get real-time data as much as they want to, and they do trend these pumps, so they do get an idea. Because what we want to do is we want to make sure that we get equal run time. So we have an hour set on this drive. This drive will run for so many hours. It will go ahead and shut down and move itself into that N3 position. Next pump will start. It moves into N1 position. The other pump is N2, so on, so on, so on, so that we get equal runtime throughout the year.
Yeah. So hey, we got a lot of redundancy. We got a lot of backup in case there is some type of failure. We also have a giant diesel generator in the back.
Yes.
So this place is designed to run throughout any kind of significant event, any kind of power failure and such. But how does Harmonics and managing that and a huge generator all come into play? I'm sure it makes things more complicated.
Well, it makes things more complicated because what happens is when you're dealing with an active filter or a low harmonic drive, whichever one, you have multiple zero crossings, okay? Well, the generator is counting those zero crossings to try to sync up its waveform, so it makes it hard for it to move into functionality because you have so many zero crossings. So it's a timing sequence that we had to set up in the generator. And we had to set it up in case all 3 pumps were running, because in the event that we did have a situation where we lost power, we don't want to leave people without water. People can live without power. People can't live without water.
Yeah.
So we want to make sure that they're able to do that. So we had to kind of take the point of view of, okay, when this comes back on, all 3 drives are going to come up and run. So we had to time the generator to handle all 3 of these loads. Now, we don't have inrush, so it's not a current problem. What it is a voltage source problem. Syncing that generator in, recognizing all 3 harmonic loads, and syncing in and turning power on so that the transfer switch can make.
If the generator's running, are we cleaning that power with the filter back to the generator?
Yes, we are.
Or are we worried about that?
Yeah, the filter is always in the circuit. The ATS is right off the generator as well as the outside utility transformer. Comes into an automatic transfer switch, and it doesn't matter. If we lose power, the transformer is offline, obviously, and then it goes ahead and syncs up the generator. The generator comes on online, and it goes ahead. If you'll notice, the main power comes in and drops into the filter before it hits anything.
Yeah.
So anytime we are running drives, we are on the active filter.
Okay. All right, hey Jeff, we got a lot of power coming in. We could potentially have a lot of power coming out. We've got an automatic transfer switch here. Kind of walk me through what we're doing there.
Well, what we do is it's a voltage source. It looks at voltage sources. It looks to make sure, for one, that the generator is not running, but it's also monitoring utility power. The utility power comes in. As soon as it senses either a brownout or a complete blackout, what happens is we go into a 100 millisecond transfer. Once we do that, but what happens before that is the generator will come up, speed up to speed, and it will go ahead and be at a rotational value that it can negotiate waveform. Once it does that, it makes that transition, and then now we're on generator power, and we are no longer looking at utility power.
Gotcha. When that transfer happens, are the pumps and the drives going to ride through that?
Absolutely.
Okay. Walk me through that.
Well, what the drives have is they have about 1,000 microfarads per phase of capacitance. And so I've got about a 5 to 10 second ride through that the drive will not trip on. And during that period of time is when the transfer takes place. And we do that in less than a second. So the drives will probably never ever fault unless there is a problem negotiating between utility and generator. And then we want them to fault. But they normally will ride through and not shut down.
So this automatic transfer switch, that's just basically saying once we lose power from the utility, we're kicking the generator on. And we're gonna do it as fast as we possibly can without interruption in any kind of pumping or motor or drive.
Correct, because the SCADA system, no matter what, it's on its own power supply, and it also has a battery backup, so it will never drop during that transition period. So even if we do have a problem negotiating the load between generator and utility, what will happen is those run commands will stay there. The drives themselves are set up for an automatic restart. So even if I do fault, every 10 seconds I'm going to try to retry. As I try to retry, as long as that voltage comes back up to a level that satisfies the drive will go ahead and restart. We have them set up to restart into a coasting load. So if that pump is still rotating, we turn on, we negotiate with the rotor, and we go ahead and turn on at whatever speed that it's actually spinning at.
We can pick up what that speed is, match it, and then carry it on from there.
Gotcha.
Tell me this, we got switchgear, we got 3 600 horsepower drives in there. I saw a transformer in there, I think. We got a lot of power in that little tiny room. You know, we're probably creating a lot of heat too, and tell me about that, electronics and
right, what we ended up having to do is when we started sizing the drives, that was one of the things that we had talked about, and we had anticipated that we would have we have about a 5-ton air conditioner, but in this environment, we're in a rural area, you get a lot of dirt, a lot of garbage, it freezes, so it's not really what we want to rely on for cooling. So what we did is we took all of our equipment and we applied our Watts loss calculation to it. And so what we ended up having to do is we went to a larger drive, derated it, and then allowed for us to go ahead and run at what we call 60 degrees C.
Okay.
Normally they would be at a 40 degrees C. These drives are rated at 60 degrees C.
And that's 60 degrees Celsius.
That's 60 degrees Celsius.
Our cabinet can run full load up to that temperature.
Up to that temperature and beyond for a short period of time. But up to that temperature, I'm going to be operating and be comfortable. And we have fan and filters that we do go ahead and turn on, and those are thermostatically controlled.
Okay.
It's a very large generator. And so what they did is sound attenuation became a big deal because, like I said, we're in a residential area. So the generator itself, when it turns on, it will actually sound an alarm first so that it doesn't startle any of the residents. And so it'll go ahead, it'll send out a small beep, it will go ahead and start, and then everybody's aware of it.
Yeah. So. Thanks for the field trip, and thanks for showing us what we do. We do some pretty cool stuff.
Yeah, this is way outside of commercial.
Yeah. Hey, thanks for checking us out on Mechanical Pros. Make sure you hit that like, hit the subscribe, and come back and check us out next week.